Uh, Dear friends, welcome to the second lecture of our differential geometry course. I'll start uh, by reminding you the theorem we have stated and proved last time. So let me just state it one more time. Theorem was basically this. So let G be a function from R3 to R, a differentiable function, and see a real number uh, let M be the inverse image of C, so this consists of triples x, y, z in R3, so that G of x, y, z is equal to C. Then the statement was the following: if the differential of G, which is just partial derivative of G with respect to x dx, partial derivative of G with respect to y dy, and partial derivative of G with respect to z dz, if this is not zero at all points of M, of the subset M, then M is a surface in R3. So this theorem is a good source for obtaining surfaces in R3. Okay, now let's apply this theorem to the example we have discussed last time, namely the unit sphere examples. So example, so let G be the following function: G of x, y, z is equal to x square, y square, z square minus 1, or actually we can just leave it like this, and let C be the real number 1. Okay, then the inverse image of 1 under the function G is nothing but the unit sphere in R2, x, y, z, triples x, y, z, so that x squared plus y squared plus c squared is equal to 1. Okay, now we have already seen that this is a surface, but this theorem will show us that this is a surface actually in a simple way. How? Well, note that the differential of G, which is x derivative of G with respect to x dx, y derivative of G with respect to y dy, and uh, z derivative of G with times dz, this is equal to what? This is just 2x dx plus 2y dy plus 2z dz. And if and if let's say p1, p2, p3 is on the sphere, then or maybe I should better use, let's say, x0, y0, z0, then x0 squared, y0 squared, z0 squared is equal to 1, so it is not 0 in particular, and thus so that at least one of x0, y0, z0 is not 0, and is not right. At least one of them is not 0. So this implies that dg, which is just dg at this point, what is this? This is just 2x0 dx, 2y0 dy, 2z0 dz is not a 0, 1 form. Okay. Hence, by the theorem, by the theorem, uh, S2, which is just the inverse image of 1, is a manifold, is a surface in R3. All right. Now let's see what we have. Okay, we have another example. This will be also an important class of example uh, in the study of surfaces, namely surfaces of revolutions. So let me explain what this is. Let C be a curve in the xy plane. So in 3 space, but it lies on the xy plane. If Q1, Q2, Q3 is a point on C, then rotating uh, then uh, rotating this point about the x-axis, we obtain the curve. I will explain this now. Q1, Q2 cosine nu, Q2 sine nu, where nu is an angle between 0 and 2 pi. So let me explain what we have. We have the 3 space here, and we have the xy plane, and let's say this is the z-axis, and I have a curve C in the xy plane, and we have a point. Let me denote it like this point Q. This is the point Q1, Q2, and 0. It's in the xy plane. So I rotate this plane, curve about the x-axis. So this point will sweep a curve like this, right? If I rotate this about the x-axis. So this way we obtain, rotating all the points on the curve, we obtain, of course, a surface, right? Like this. So this is the surface of revolution. All right. Now let M be this surface. So let M be the surface obtained by revolving C about the x-axis. If let's say C is given by this equation y equals f of x, so suppose it's a graph of a function in the xy plane where f is a function defined on some interval, let's say ab, on then a parameterization. So my q, this point q1 q2 0 is this, then it is some uh, t, x coordinate is t, y coordinate is f of t, and z coordinate is 0. Okay, so here you see that in the xy plane my curve is like this. Okay, so if this is t, then this coordinate is f of t. Okay, so rotating this, we will obtain a surface in R3. And how it is given? Well, rotation in the about the x-axis means rotation about the, sorry, it's a rotation in the yz plane. So yz plane, this means I am just rotating this point 0, sorry, f of t, f of t 0 in the yz plane. So in the x direction, nothing changes, right? X coordinate doesn't change. As you move this point, x coordinate doesn't change, right? The x coordinate here is fixed. So this is, say, q1. It is fixed. So I have this matrix then, and I rotate mu radians. So this is cosine mu minus sine mu. No, x coordinate doesn't change, so I have 0 here. Here I have cosine mu minus sine mu, and then 0 sine mu and cosine mu. Okay, so this is my x t nu. And what is the result? Result is, okay, t, and then t times cosine nu minus f of t times sine nu, and uh, t times sine nu plus f of t times cosine nu. So this is the sorry, I made a mistake, I guess. Yeah. Sorry, I did the matrix multiplication not correctly. So, okay, 0 t times this, okay, and then 0 and yeah, this is, sorry, uh, f of t times cosine nu, and then 0 and f of t times sine nu. Okay, yeah, all right. Okay, We will see in the next section that this is a surface patch. Uh, we will see that this xt new is a proper surface patch in the uh, next section. Okay, let's see now. Uh, Before I finish this section, let me give you some other examples of surfaces. Let me start with the torus. We will study these surfaces in more detail in the coming up lectures, but let me just now, for time being, uh, introduce you these surfaces. So this is 2 torus. We denote it by T2. Note that this is obtained by, actually, this is the surface of revolution, right? If you take a circle like this and rotate this circle, uh, let's see, about the z-axis. So like this, about the z-axis, what you will get is this surface, which is the 2 torus. This is the surface of revolution, right? Just rotate the red circle about the z-axis. Here is the z-axis. Let me put the axis, coordinate axis. Okay, so this is the z-axis. Let's say this is the y-axis and this is the x-axis. This is one example. Another example of surface, we have orientable surfaces of this type. So this is a genus 3 surface. This has one hole in it. Therefore, it has genus 1. This is a genus 3 surface. So G is the number of holes uh, and called the genus of the surface. Okay, so torus is the genus 1 surface. This is the genus 3 surface. These are orientable surfaces, and there are non-orientable surfaces. A famous example, you probably heard this before, the Möbius band. Okay, Möbius band. This is an example of a non-orientable surface. Okay, non-orientable surface. Non-orientable means you cannot distinguish two sides of this surface. Okay, one side is up, which side is up, which side is down, or which side is in, which side is out. You cannot distinguish. Therefore, they're called non-orientable. Okay. Now let's pass to the second section, namely patch computations. We will do some basic computations. We will see basic computations on surface patches. All right, let's start with a surface patch. Let X be a surface patch, and U0, V0, a point in the domain of the surface patch. Then the function, the functions actually, these functions, sending U to the following curve. I keep the second coordinate fixed, just change the first coordinate. So this defines a curve in 3 space, and this function V is mapped to U0, X of U0, V. So this time I keep U0 fixed and V uh, as a parameter. So these two functions define two curves on the surface passing through the point X of U0, V0. Okay. I have a definition at this point. We will consider the velocity curves of this, velocity vectors of this curves. The velocity curves, not curves, vectors, the velocity vectors of the above parametric curves, these curves. So let me emphasize them. Are denoted, so these velocity vectors are denoted by d du x of u v0. So I take u derivative of this function at u equals u0. So this is nothing but x sub u, right? This is just partial derivative at u0 v0, and the second one d dv x of this time u0 v, v equals v0, so this is x sub v u0 v0. Okay, at this point we may just draw a picture. So let me draw the picture. Okay, so all right, so let me draw our curves. Okay, uh, and our velocity vectors. So this is x sub u0 v0. This is x sub v u0 v0. Uh, this is the curve. Maybe I use a. Okay, so this is the curve. Sorry. Let me use this. Okay, so this is the curve uh, x u v0, right? And this is the curve x u0 v. Okay. What about this point? This point is, of course, the point x of u0 v0. Okay. And these are the velocity vectors of this curves. Here the parameter is v, and on this curve the parameter is u. v0 is constant, u is the parameter. All right. If our coordinates in the coordinates uh, if xuv has, if it can be written like this, x1 x2 uv and x3 uv. So the xyz coordinates of the coordinate patch x, then of course what is the uh, velocity vector xu? So it is just the partial derivative of this function with respect to u. Well, that is just, of course, partial derivative of each coordinate function with respect to u. So x1 del x1 del u, del x2 del u, and del x3 del u. And the velocity vector x sub u is just del x1 del v, del x2 del v, and del x3 del v. So these are the coordinates of the velocity vector x sub v. Okay. Okay, let's consider some examples again. So first we consider again the unit sphere example. The unit sphere. Uh, Last time given we had given some coordinate patches for this using Cartesian coordinates. Now let's consider a different coordinate system, namely spherical coordinate system for the unit sphere. So using spherical coordinates, we get uh, the coordinate patch xuv Okay, what is this? So this is well, okay. This, I don't take the unit sphere, but uh, the sphere uh, with center at the origin and radius r. Okay, so coordinate patches then are just cosine r times cosine nu cosine u r times cosine nu sine u and r times sine nu. Let me draw you the uh, sphere we are talking about. Oops, sorry. Okay, so this is the z-axis. This is, let's say, uh, x, y, and z-axis. So whenever I have a point here, let's say x, y, z, its projection onto the xy plane is here. Okay, so okay, now this distance is r. This angle is u, and uh, all right, so this angle is nu. So that this is r times sine nu, which is the z coordinate. Okay, so x is this, y is this, and z is this. All right, so u is this angle, and nu is the angle drawn from the xy plane to the line joining xyz to the origin. Okay, so this is our picture and the coordinate patch. All right, then here, of course, u is ranging between minus pi and pi, and nu is ranging from minus pi over 2, pi over 2. Okay, so if you have, for example, a coordinate patch in the u nu plane like this, then on the sphere, this corresponds to something like this. Okay, let's say this is okay. So it corresponds to probably something like this. Okay. Okay, now let's compute the velocity vectors. So this is x of u nu. R is a constant here, the radius, right? The variables are u and nu. So when you take derivatives with respect to u, you get what? Minus r cosine nu sine u, uh, r times cosine nu cosine u, and uh, u derivative is 0 here, and derivative with respect to nu is minus r sine nu cosine u minus r sine nu sine u and r times cosine nu. So these are the velocity vectors. Why actually this function defines a proper surface patch? We will see it in a minute. Okay. Before I show that this really defines a surface patch, let me give a definition. This is a relaxation of a surface patch, and we will call it as surface parameterization. So again, a regular mapping x from D to R2, whose image lies in a surface M, is called a parametrization of the surface of the region x of D of M. Okay. So what's the difference between a surface patch and a surface parameterization? Well, the only difference is that they are both regular, but we don't require here that it's a one-to-one mapping. So a coordinate patch is a one-to-one proper parameterization. Okay. All right. So let's continue our example. So here we had this velocity vectors. So back to the above example. Uh, the spherical parameterization defined above is not one-to-one in general. Why is that? Uh, because if you increase since since x of u plus 2 pi, right? So if I increase one angle 2 pi radians, then the image will not change, because here I have all trigonometric functions and they are periodic with period 2 pi. Okay, so they are not surface patches if we define them not careful enough. If we choose big domains containing both a point pi nu, u and nu, and u plus 2 pi nu. However, on a small uh, piece of the plane, they are one-to-one. Okay, well, why this is regular? Why is x regular? Well, to check whether it is regular or not, we have to compute its derivative. But we can do actually something simpler. You see, the derivative map is given in coordinates by the so x uv, right? x1 uv, x2 uv, and x3 uv. And the derivative map is given like this. So the first derivative with respect to u, uh, and the second coordinate with respect to u, third coordinate with respect to u, and then derivatives with respect to no, I should be more careful. Del x del u, del x1 del nu, and then del x2 del u, del x2 del nu, right? Del x3 del u, del x3 del v. And I need to show that this matrix has rank 2. In other words, the linear map defined by this, right? This linear map defined on uh, the tangent space in D, and uh, the image lies on the sphere, right? So this map needs to be, so must be one-to-one. Well, this means the rank of this matrix should be 2. Well, it has 2 columns, therefore rank is 2 is equal to saying that the columns are linearly independent. And to check that the columns are linearly independent, you see uh, these columns, this is nothing but uh, so this is x sub u and this is x sub v, right? To show that these are linearly independent. So in other words, the columns xu, xv must be linearly independent, but this is equivalent to showing that, however, this is equivalent to showing that how can you show that two vectors are linearly independent? Well, we just take their cross product and show that it is not zero. Okay, so let's compute the cross product. Well, here is my vectors, velocity vectors. I will take the cross product of these two. So here I do the computation. Well, both rows have R component in them. So I take R out. So two R's coming out will give me an R squared. So this is R squared. And then let's say I have here I, J, K, or U1, U2, U3. And then the coordinates, first coordinate was minus cosine nu sine u. Here it was cosine nu cosine u 0, and then the third entry is sine nu cosine u minus sine nu sine u, and then here I have cosine nu. Okay, this is the x sub u, and this is x sub v. Right, yes. And if you compute the determinant, right, let me tell you what you get. You get r squared times cosine squared nu cosine u, cosine squared nu sine u, comma cosine nu sine nu. And if you compute the length of this vector, so if you take squares of the components, sum them up, and then take square root, you get r squared cosine squared nu, and this is not zero, provided that the angle nu is in between pi over 2 and pi over 2. Okay, that's why here we considered the variable nu only in the interval minus pi over 2 plus pi over 2. This means that this angle goes from uh, minus pi over 2 to plus pi over 2. So it excludes the pole points, south and north pole points, where the angles are pi over 2 and minus pi over 2 namely. If you want to consider a parameterization for the North Pole and South Pole, then you have to choose a different parameterization, playing with the coordinates. In particular, so uh, x is regular, and hence a parameterization. Okay. Okay, I'll do one more example, but let's do it next time in the next online class. So let's stop here and I'll see you later.